All righty, fantastic. Okay, well, I wanted to talk to you about lights in the sky, the daytime sky. This is a presentation I first gave 10 years and 1 month ago. It was January 9th, 2012 was the first time I gave this, and I don't know if I've done it since, but it's certainly time to do it again. I see what Diane does and in the Master Naturalist, and it's plants and animals and stuff, but there's other things that you can see in the world that are really interesting, and that maybe you can talk to the public that you deal with and show them the sort of interesting things that are going on around, at least a couple here that don't have to do with animals or plants. Now, there's all kinds of weird things that happen in the sky, and I'm only going to talk about a subset of them, like the ones that you can see around here. So most of the pictures that I'm going to show you are ones that I've taken, and most of them are local, like from my front porch. And it's not because I'm a great photographer or I have a special vision or anything. I just want to show that these are things that anyone can see here. So for instance, I'm not going to show any pictures of northern lights. They're lovely, but it'd be a bad day if we could see them here. And I'm not going to do stuff like Marfa lights and UFOs and stuff like that. But there's a lot of really interesting stuff that goes on in the sky that most people don't see because they just don't look up at it. Okay, so let me start off here. What I'm going to do is start off first talking briefly about what light is, because that's what we're dealing with here. And there's not a lot you need to draw from this slide. I mean, there's so much physics that goes into light. I'm not going to touch on that. Light is something called electromagnetic radiation. It's something that has electric effects and magnetic effects, and radiating, it means it moves. Sometimes it behaves like particles, which are called photons. Sometimes it behaves like waves, and we can leave most of that out. The only parts you need to really get at for the rest of the talk are that there's something electrical here, that it can react with anything that has an electrical charge, like a cat. Hello, cat. Like our cat has arrived to help. Something with an electrical charge, like an electron on an atom. And the other part that's important is that there's a wavelength associated with it. It's something that's waving. Don't ask what, but there's a wavelength that's associated, and that's an important part. So that's all the physics we need here. Light is part of this huge span of electromagnetic radiation, and it's only a small part that we can see with our eyes. The visible spectrum here from purple to red, and the wavelength of that is pretty small. It's 0.4 to 0.7, about a half of a micrometer, or a half of a thousandth of a millimeter. It is pretty small, and you can't see it. And there are ways of measuring it, but that's not important here. But that's all we can see of it. And where's my cursor gone? But there's a lot of other parts to the electromagnetic spectrum, they call it. At shorter wavelengths, you get into ultraviolet light, which is what gives you a sunburn, X-rays, or even shorter wavelength. At longer wavelength, infrared light, this is light that behaves very much like the light we can see. It just, we can't see it. So this is what your TV remote uses to turn your TV on and off. Longer wavelengths than that, you get into heat radiation and radio waves. So it's a huge range of phenomena that are all basically the same stuff of electromagnetic radiation. And just for comparison, for size, and there's the usual pollen that might bother you, ragweed pollen, 20 to 30 micrometers. It's quite big compared to the wavelength of light. Mold spores are much smaller at about 5 micrometers, and microbes like E. coli are almost the right size. They're about 1 to 2 micrometers. So we're talking about very small wavelengths here. Okay, so let's start talking about the phenomena themselves. The first one, really familiar. This is blue sky. And we've all seen this. The slide on the left is one I pulled out of my archives. This is when Diane was working up at Mason Park doing a wetland restoration, building a wetland there. And it was a gorgeous day with a beautiful blue sky. So why is the sky blue? Well, it's blue because the electric part of light, the electric part of electromagnetic, interacts some with electrons in atoms in gas, for instance. Hey, Diane, are you up there? Could you come and let the cat out? Sorry, life goes on here. And it's just what's one of those facts that the blue light interacts more with the atoms in air than red light does. So when you see this beautiful blue sky behind you, it's light from the sun that's come into the atmosphere, bounced off of gas atoms right and left and back and forth, and ends up coming to your eye from a direction that's not from the sun. So the sunlight has less blue than when it entered the atmosphere. And in fact, the sun looks sort of yellowish, and if you were in space, it would look much whiter because there wouldn't be air in the way. So the blue light gets scattered around. Actually, ultraviolet light does too, and so it's possible to get a pretty decent sunburn if all you're exposed to is just blue sky. So that's sort of what this diagram on the right is meant to show. But let's think about the other half of that. What happens, when the sunlight goes through lots and lots and lots of air, and that would be like at sunrise or sunset. And at that point, when the sun has gone through lots and lots of air, most of the blue light has been scattered away from it. And what you're left with is primarily the red. And of course, that's why you see sunsets being red. The picture on the left was just a stunning day. It was raining like crazy, but the sun was out. It was just sunset. And this is our street from our upstairs balcony. And you can see the street down there. And here's the gutter full of water. Just raining like crazy. So we had this gorgeous orange light from the sun, and it was being bounced all around by the rain, the raindrops coming down. So, that was just gorgeous, but that's what's left over after all the blue light gets reflected to make blue sky. Okay. Next, you get a little bit larger particles, dust particles. And here, I mentioned that I work on the Mars missions. I've been very lucky to be involved in that. And here are a couple of pictures of what the Mars sky looks like. And it is not blue like on Earth. It's more sort of squash colored, butternut squash colored. And that's it. Of course, there's air on Mars, not so thick as ours, but the sky is that color because it's loaded with dust. Mars is so dry, there's no rain to wash the dust out of the sky. And so it's there all the time. And the color you see there is the color of the dust. This happens on Earth too, of course. You get smoke clouds and dust clouds, and every now and again you get one of those clouds of dust from Africa that blows over us. But the cool thing about this is that when the particles, these little dust particles, are about the same size as the wavelength of light, there's some really weird physics, weird effects that happen, which I can't explain. But anyway, this is what it ends up being. On the upper left is a sunset on Mars, and it's blue. It's just the opposite of the Earth. On the Earth, we have blue skies in the daytime and orange sunsets. On Mars, because of this weird dust, they have orange skies in the day and blue sunsets. And this happens occasionally on the Earth in just the right conditions, just the right amount of dust. And on the right here is this picture I found on the internet. Of course, it's Egypt, the Great Pyramids, and there's the sun setting at a blue sun because the dust is just the right size. Sometimes this happens at night, and so you get real blue moons, not this, what they call blue moons now would be like the second full moon in a month. But sometimes they actually do look blue, and it's because of this, because there's just the right amount, right size of dust in the atmosphere. Okay. Let's see, next would be, with larger particles, you start getting into some weird stuff where, like here's light coming into at a little particle, and the light sort of bends around the particle and spreads out and makes these funny patterns downstream. And if I can be allowed, I'm going to drop out of the presentation and try to do a demo. This is something I've not done on screen before, so we're going to gamble a bit and see if it works, okay? Okay, so I'm stopping sharing, and there I am. What I've got is a green laser to be our source, where am I? To be our source of light. You can see it on my hand and stuff. And I've got a couple binder clips and a piece of metal in there with a little gap in between the two pieces of brass metal in the middle. And so that's going to sort of be like a little particle in the air. And so with any luck, what I'm going to do is I'm going to shine the laser light on this piece of paper back here. Can you see that? Yeah, I guess. Let me turn out the room lights.
Yep.
Okay, you got that? That's just
We can
the
see
laser itself. So I'm going to take that light and I'm going to move that little slit in front of it. And there you can see the shadow of the metal. And look what happens when the light goes through that little slit. Can you see that? It gets all spread out. See, try it. I'm missing it. There we are. You see that it's getting spread out right and left and that there's spots along it?
Yes, we can see that.
Fantastic. That is exactly the phenomenon exactly what's happening with little particles, with these little bigger particles in the atmosphere. And here I had a hole for the light went through. In the presentation, it's a particle, the light goes around, but it's the same deal. The light gets spread out. So let me go back to sharing here. Okay, so there we are back there. You've now seen this happen. This is an effect called diffraction. And longer wavelengths of light, the redder colors, make broader spread in diffraction. And so, you know, if the blue is close, if the blue is a smaller spread and the red is a wider spread, you can imagine you could get bands of color out of this. And in fact, that's exactly what happens. And so here's an example from our front porch. That's our sweet gum tree in the way, and the edge at the top here, that's the bottom of our little balcony on the second floor. The sun is up here somewhere. And here you can see these diffraction rings around the sun, reds and blues and reds and blues. This is sunlight going through some thin clouds that are all little water droplets of all about the same size. And this is called a corona. It's where the sunlight diffracts off of small particles. And this kind of thing is really common. You can see it maybe half of the days where there's a bit of cloud in the sky, but no one looks at it. Here are a couple others we saw on the left side. There's another one of these circle things. That post sticking up in the middle is the post that our mailbox hangs on. And I just did this so that it would block out the sunlight itself and it wouldn't overexpose the picture. When it's not so concentrated and circular like that, it's called iridescence, and clouds do this fairly frequently. The image at the bottom I took at Armand Bayou Nature Center rather a few years ago. It was on one of those times we were doing a prairie burn. So I had my camera along and happened to look up, and there's this gorgeous, gorgeous pink cloud in the sky. And it was all from the sun, which was over that direction. So this is fairly common. You ought to take a look. Sometimes you have to hold your hand up to block out the sunlight, otherwise it's too bright. Or my wife has a pair of sunglasses that are pretty strong, and sometimes that's enough to help you see it real well. That's a pretty common thing that you can see. It's just from drops, from water droplets in the clouds. Now, when you get to bigger droplets, you get rainbows, or can get rainbows. And this is a one that an image I took when we were traveling up to Toronto to visit some of our relatives-in-law up there. And I'm sure you've all seen rainbows like this. This is a pretty good one. You got a pretty bright lower rainbow, red on the outside, blue on purple on the inside, and then a second bow outside of that. So these are pretty common. So let me just talk about how they happen. These are a different phenomenon from diffraction. This is called refraction, and it's happening when the light goes into the raindrops. The raindrops are big enough that the light can go into it and bounce around inside and then come out. And it's sort of like a prism in the upper right here, where the light can go into the prism and it gets divided out into the colors, red, yellow, green, blue, like that. So what this diagram here is showing is your eye and a couple stylized raindrops, these circles, like a cross section of a nice spherical raindrop. So in this raindrop, for instance, colored light from the sun comes in here, gets refracted into the drop, and the different colors of light get bent at different angles, and that's the critical part here. So the light gets bent, where's my cursor? Light gets bent at different angles, bounces off the backside of the raindrop, comes up to the front and gets bent again. And the way they've drawn this one, the red beam from this raindrop is coming to your eye. For the other raindrop up here, the same kind of thing happens, but it's displaced a little bit in space. So instead it's the blue beam that refracts and comes to your eye. So what you see is higher up in the sky, where you're looking this direction, you see red, and a little bit lower, looking this direction, you see blue. And that's what this diagram is trying to show. And that's exactly what you see in the real rainbow, that the red is to the outside and the blue is to the inside. Okay? So why is there a bow? What does this arc mean? Well, that has to do with there being drops all over the place in space. The upper diagram here, there's your eyeball again, and the sun is behind you. A raindrop that's like here, what you'll see is the red and blue light from it coming from like sort of the top of the arc here. This raindrop is meant to be closer to me, closer to the camera. So what you see from that, where's my cursor? There it is. What you see from that is over here on the side of the rainbow. And in fact, if you were up in the air in an airplane, you would be able to look down and see the same kind of thing happening down here at the bottom. So the rainbow is actually part of a big circle of light that's refracted from raindrops. And the center of the circle is exactly opposite. The sun and your eye are in line to the center of that circle. So if you were up in an airplane looking down at clouds, sometimes you might be able to see the full circle rainbow. Of course, we never see that on the Earth's surface. Sometimes it's possible you can see maybe more than just the half circle if you're way up on a top of a mountain. But something that can happen, that we're very lucky. Mostly you see rainbows sort of late in the day, thunderstorms and all, and so the sun's fairly low, and so you see this beautiful big arc in the sky. But imagine what would happen if the sun were higher in the sky. Well, then the center of the circle would be lower and lower and lower, and eventually maybe only the top of the rainbow would be visible above the horizon. And we actually saw this on one of those birding trips down to the Amazon, and that's the picture down here, where this is the Amazon. far bank of the Amazon, and there's this rainbow that's just about to dip below the horizon. Got the red and the yellow and the blue. Those ought to be visible here. I've never seen one, but they ought to be visible. Okay. Oh, and then the other thing, of course, the double rainbow. It's the same idea, except now the light goes into our little spherical raindrop here and bounces twice inside. Remember, for the main rainbow, there's a single bounce off the inside of the raindrop. For the outer rainbow, it bounces twice, and the colors sort of get reversed by that second bounce. So you see red on the inside and green on the outside. Okay, well, I'll stop there for a moment. Does anyone have any questions to this point? From here on, I'm going to talk about ice crystals.
This is really great. This is great, Alan, but I'm not seeing any questions right now. You must be being totally clear and everyone's
totally clear, or nobody understands a thing I'm saying. That would be my fault. All right, well, let me go to ice. Ice is just fantastic. It does so many weird things with lights in the sky. And mostly you think of ice and snow being in this beautiful snowflake shape in the upper left, but it's hexagonal because that's what ice does. But it's got all kinds of decorations and plumes and fern-like things on it. Those are really beautiful, but they don't do much in the way of sky effects because they're too complicated. The light bounces all different ways around them all. Most of the stuff that ice does in the sky is from little crystals that are very simple. And this is a crystal I stole from a book about ice stuff. There are two basic forms here. One are like this here, little flat hexagonal plates. They're six-sided. They're much thinner than they are wide. Those plates. The other kind that you see here are hexagonal columns. This is a good one where you can see the three faces very nicely there. And those are the two that make most of the really interesting ice displays. Now, you might think down here in Texas, we don't see very much of that. Well, it's quite possible in a couple of days we'll be able to see this once the storm goes away and we get some sunlight. But actually, these are fairly common even here because it gets very cold very quickly as you go up in the atmosphere. Maybe by 5,000, 10,000 feet up, it's already below freezing. So if there are clouds up there, cirrus clouds, which are mostly ice crystals, they can give you these wonderful ice effects. And almost all the pictures I'll show here I've taken here in town. So if I can see them, you can see them. Okay, let's start off with the first one is pretty. Oops, where have I gone? Pretty simple. Those nice flat ice crystals like that, those can act like mirrors. And so the sunlight can come into one of these ice crystals and just bounce off the surface of it and bounce back to your eye. And these flat crystals, and it sort of matters how they are oriented in the sky. Flat plates like that tend to fall pretty flat. I mean, they don't fall edge down. They'll tend to fall pretty much horizontal with the flat side horizontal. And you can sort of see that like if you take a leaf or something and a dried leaf and let it fall. It doesn't just fall straight down clunk. It goes back and forth, mostly flat. And that's sort of what these crystals do. So you can get sunlight reflecting off of these crystals to your eye. And so like if the sun is from this direction, what you see with your eye is up above it. And this produces a vertical shaft of light above or below the sun, sometimes the moon, sometimes you can see it with lights, lamps in a parking lot or something. And okay, the picture on the left is a really good one. It's not something I took, it's one I found on the net because I don't have any real real good ones of this phenomenon. But you can see the sun is here sort of behind that cloud. And there's this pillar of light above it and below it. And what you're seeing is light reflected off these little flat ice crystals in the sky. We took a little vacation last month, Diane and I, up to Wisconsin to visit our son who lives in Madison. And there I saw something of it. This is at sunset, and there's a bit of a sun pillar right here above it. Of course, it's red because it's sunset and most of the blue light has been scattered out of the sunbeam. So you're seeing a red pillar. Okay, that's one. This is another one, really, really common. This is a 22-degree halo around the sun. And the sun is behind my hand here, and I'm holding it there so I don't overexpose the camera. And this is our neighbor's roof, so it's just on our front porch. And you can see in the sky, there's this circle, this halo. It's slightly colored. These are really, really common. And they form from, they form from these hexagonal column crystals where the sunlight will come in one face of it and then come out two faces over. And again, there's some refraction that separates the colors out. And so here's just sort of a diagram on the right of how this works. There's your eyeball, and all these crystals, these ice columns floating through the sky will refract the light, all of them about 22 degrees away from the sun. That should be just because of how ice refracts light. Now, 22 degrees is actually a pretty easy angle to deal with. If you take your arm, hold out your arm straight away from your face, and stick your thumb and pinky finger out opposite directions. The distance between the tip of your thumb and the tip of your pinky is about 22 degrees. This is something that Diane has talked about for astronomy stuff too. So if you were to see the sun and put it right behind your thumb, this circle would be about where your pinky is. Now, let's go back to Mars here. Because for the first time, like last month, one of the Mars rovers has actually seen one of these halos on Mars. And this was, sometime in December, I believe. They took pictures of the sky, and on the upper right, here's just the plain picture. You can see the sun and the overexposed blob in the camera. And then there's this sort of ring around it here. And the folks that do these cameras worry a lot about all kinds of artifacts. I mean, stray light can get around in the cameras and make all kinds of strange things, but they're pretty sure that this is actually a 22-degree halo, an ice halo on Mars. And on the left side, this is like a fisheye lens view of the whole sky. So this is the horizon going all the way around. This is in Jezero crater on Mars. So, and we can do angles here too. From one side of the sky to the other, that's 180 degrees, half of a full circle. So 90 degrees right up top in the sky would be about in here. Okay. Halfway from that 90 degrees to the horizon, that would be like 45 degrees. So the sun's about at 45 degrees elevation in this picture. And then half the distance, my cursor keeps this, half the distance between 45 degrees and 0 degrees is 22 degrees, and there's our halo. So it's pretty sure that this is a water ice halo on Mars. They're really rare there, partly because of all the fine dust in the atmosphere. There's so much dust that when the ice can grow on it, there's so many places where the ice can grow that it never grows big enough to make one of these halos, to get big enough to refract the light. So this is very rare, but it's happening, it happens on Earth, it happens on Mars too. Okay, next one. Another really common thing is a sundog. And this is again at home. Sun is over here behind the neighbor's trees. I've moved so that it's not blasting out the camera. And at the same elevation as the sun, over left of center, there's this bright spot and a little bit of color. That's a sundog. And they're pretty common. They come on both sides of the sun. I only show one here. And they're caused by, again, by these hexagonal ice crystals. And I'll show this here, sort of the squat hexagonal ice crystals. The sunlight comes into them, and it's really sort of the same thing. It comes in one face and leaves, leaves two faces over, gets split apart into the blue and red rays. And this will make the sundog at 22 degrees away. It's the same 22 degrees that is the 22-degree circle. The other thing that can happen with these sort of squat crystals is the sunlight can just reflect straight off onto their surfaces. And so there won't be any color with that because it's not refracting. The light isn't going into the crystal. And that'll get spread all across the sky, but always at the same elevation as the sun. So this is next, I'll show this, and this is a picture. It's unfortunately not mine. I wish I'd seen this display. This is up in Alberta. It's winter, stolen from the web. And you can see pretty much all of the stuff we've talked about so far in this picture. The sun is here. Above it and below it are sun pillars, which are by the flat plate ice crystals. You can see the parts of this 22-degree halo, which are from ice, from hexagonal prisms of ice that are oriented every which way. You can see the sundogs here and here, which are from flat plates that are oriented, that are refracting the light. And you can see pretty strongly this perihelion here, the straight line here, which is from reflections off of those squat hexagonal prisms, all at one time. It was a beautiful thing. I wish I'd seen that. I haven't seen anything like that myself. Okay. Next, I'm going to talk about some less common ones, but they're really, really cool. And again, I've seen them here. This is called a tangent arc. The sun is down here. You might recognize this tree again. We've seen it before. Here is a very weak 22-degree halo, and that there's this bright blob up here that sort of runs up and left like this. This is called a tangent arc. It's called that because it's tangent. It touches this 22-degree halo. And this is caused, but it's by the same thing. It's by these hexagonal ice columns, but now they're floating horizontally. They're not oriented randomly like they would be for the 22-degree halo. They're all sort of floating horizontally, and they produce this effect. And if the sun is high enough, you can see the same thing below the sun, and that's what, hello, that should be, whoops, I missed something. There we are, this picture. And I took this in Albuquerque. I was visiting my mother when she was in memory care. And there's the sun behind the light post, and there's a very, very weak halo here. But yet underneath the sun, there's this bright colored thing, and this is another one of those tangent arcs. So it can be above and below the sun. Okay, next. This is the one that really got me going on these light displays. It's a circumzenithal arc. Zenith being the highest point in the sky. You know, if you look straight up, you're looking straight at the zenith. And gosh, this must have been maybe 2005 or something, 2006. I was outside and happened to look up quite by mistake. And there's this incredible bright rainbow up in the sky, circling a partial circle around the zenith. And I'd never seen anything like that in my life. And so I quick got out my camera, and back then it was a real crummy digital camera, and took a series of pictures here to show what it was I was seeing. And then went back and looked on the web and books to find out what it was. It's called a circumstantial arc. And that's the first one I'd ever seen, but seen a lot more since then. Here's another one, a little bit weaker at home, and that's our Magnolia Tree, again from our porch. And you can see maybe below it, there's sort of a hint of a 22-degree halo, and then a hint of a tangent arc here. I saw one on Armand Bayou during one of those burns. And here's another one we saw up in Canada. Doesn't matter where, they're actually pretty common, and they form when light goes into one of these big hexagonal ice plates, but it's not through a side. If it enters through the top face and comes out through a side face, then you get this look. These can be very, very bright, like that first one I saw. They're really pretty common, but no one ever sees them because you have to really be looking up, sort of like a rube in the big city looking at all the tall skyscrapers, but they're there. Okay. And then one other weird one. This is a superlateral arc. And this is not local. This is something I took, but it was up in Duluth, Minnesota. Diana and I had gone up there for their fall hawk watch for a while, having a lovely day until I got distracted by this funny lights in the sky. And that's the superlateral arc above the clouds. You see nice puffy cumulus clouds, and it's very thin cirrus ice clouds above it. This kind of arc forms, it's a bit like the circumzenithal, where the light comes into a ice column, these prisms, through a long face and enters and leaves through the hexagonal face. And if you'll notice, this is not a rainbow because the colors are opposite of the rainbow. The rainbow would have red on the outside and blue on the inside. This has red on the inside and blue on the outside. This is the only one of these I've ever seen, but they're still there. Okay. And I'm almost at the end. I'm going to end with a picture that I didn't take, a light display that's probably once in a lifetime or once in 10 or 15 or 50 lifetimes. It was taken in New Mexico in 2015. Whoops, back up. Fellow Joshua Thomas woke up at dawn, looked out his window and saw this. Red River's up in northern New Mexico in the mountains. It's north of Taos. And this is just a fantastic thing. These are all these arcs in the sky have to do with ice crystals. And you'll recognize a lot of them. The sun pillar we talked about, the 22-degree halo we talked about, the upper tangent arc talked about. The superlateral arc was the last one that I'd had. He did not, I don't know if there was a circumzenithal arc because I don't have a picture up there. There might have been or might not. But look at all of these other arcs, all these other displays in the sky. This is absolutely fantastic. I wish I'd been there. And the deal is, that we just talked about two kinds of ice crystals, the hexagonal prisms and the hexagonal plates, but ice can make all kinds of other shapes of crystals too. And every one of them can make its own kind of arc and display in the sky. So I always hope to see one of these, but to see any part of it, even a 22-degree halo is pretty cool. Okay, so I will end with two references for you, so you can see more about this stuff. There's a fantastic website, Atmospheric Optics, atoptics.co.uk, which has great explanations for everything I've shown and everything else there. And there's Flash page yesterday had this fantastic picture on it. This is Mount Etna erupting with the eruption and then the cloud here. and there's a pillar of light above it. This is the same as before. It's the hexagonal plates of ice. It's just in this case, the light is from the volcano and not the sun. It's just fantastic. And then there's an old book, maybe 1920s or teens or something, by Minert, called The Nature of Light and Color in the Open Air. And it's a charming book. It's an older book. It doesn't have a lot of the deep physics in it, but it explains the phenomenon I've talked about and all kinds of other things having to do with shadows and light in the sky. And I would really recommend it. I've enjoyed reading that book immensely. So anyway, that is my end finally. And I'm happy to take questions.
Yes. Gene Fissler, could you ask the first part of your question, of your first question and your second question too?
Sure. Let me see if I can remember what I asked. Let me look at the notes. So here's the deal.
Get into that age.
Here's the deal. I was listening to you. You know, this is all about water. It's about water ice, water crystals in our atmosphere. It made me wonder, as I thought of other, well, as droplets, on other planets, if there was other things in the atmosphere, other liquids that would condense, would you still get a rainbow-like thing, but with different angles and different colors?
Yeah, exactly.
Okay.
I haven't ever seen anybody talk about rainbows particularly, but there's a couple of people that have thought about, like on Mars, it's cold enough that the carbon dioxide in the atmosphere crystallizes to make dry ice crystals. And there are people that have said, okay, you know, what kind of rainbow, what kind of halos and arcs and stuff would you see from that? So yeah, on other planets like, I don't know, Titan, for instance. Titan's got all this hydrocarbon guck in its atmosphere. You ought to be able to see rainbows and arcs like that too, but you're absolutely right, because the refractive index of the liquid will be different. The rainbow may be in a different place and it might be wider or narrower. Depending. But yeah, you're absolutely right.
Cool.
That's
And then the other,
physics of light, not so much with the material itself. Yeah.
right. And then you keep talking about these hexagonal crystals, flat and columnar and all that. And then they're at certain angles. What manages or what causes them to maintain that orientation, the crystals themselves?
Yeah. Well, the water ice crystallizes in hexagonal shapes. That's just the way the atoms, the molecules arrange themselves when they freeze. And so every ice crystal has some kind of hexagonalness about it. Like that really fancy one with the fern-shaped things off the edge of it. Sometimes they get really elaborate, but it's just the way the water molecules arrange themselves when they freeze that makes them hexagonal. Carbon dioxide, for instance, when it freezes, I think it makes little cubes or octahedrons or something. It's not hexagonal plates, so it has to do with the way the atoms are arranged.
Well, yeah, but I got the impression what you're saying. The crystals themselves are all oriented north to south or east to west or flat. Is that going on? Okay.
No, I'm sorry, that wasn't the impression I meant to give. The most common shapes of the crystals are these flat plates or the hexagonal columns, the prisms. The flat plates, when they fall through the air, it's sort of hard to demonstrate this, but they tend to fall with their flat side horizontal, like parallel to the Earth's surface. They tip a little bit back and forth, but they basically tend to fall with the flat, the big side down. And so that's how you get the pillars straight above the sun and not.
Okay. All right. Super. Thank you.
I had to figure out a way to demonstrate that better.
No, you got it. I mean, I get it. It's air resistance. I understand why they do that. And that keeps them all.
Yeah. I mean, like you could just try this yourself. Take a card or a piece of paper or something and start and drop it, and it's not going to go straight down. It's going to turn sideways so that it's sort of flat looking.
Very interesting. Thank you very much.
Okay.
Sure.
Okay. Larry and Bobette Brassfield, could you unmute and ask your question, please?
Hey.
Sure. Can you hear me?
Yes, sir.
I was just curious who came up with all the names for these phenomena. You know, was it just one person or was it multiple people? Or?
It's been, you know, sort of accreted over the years as different people have described them and all. Some of them are pretty obvious, like halo. You know, it's a halo. That's no problem. Rainbow, probably that word has been around forever. Others are, let me just back up here. Like some of these are named after people. Perry, I think this is probably the polar explorer Perry. No, it isn't. It's spelled differently. But there was someone who described these, and so they ended up being named after them. There was no you know, there wasn't just some conference that came up and named these. They're just named one by one after people recognize them as being distinct.
Thank you.
Okay.
Donna, could you unmute and ask your question, please?
Yes. Are you familiar with the term green flash?
Oh, yes, absolutely.
Well, what's the phenomenon that causes that?
Okay, I think I may still have some slides. That's in the original version of this. There was, you know, this was the extra credit part. Yeah, the green flash happens just as the sun is setting. If the air is very, very still, the sun, you know, it's setting. It's mostly red because it's passing through a lot of atmosphere. And if there's a atmospheric inversion, you know, a temperature inversion in the atmosphere, that can make that temperature inversion, a density inversion, can act like a bit of a prism and can separate the red and what's left of the blue light, which at this point is only the green. So yeah, you can see this like here on the right side. There are some layers in the atmosphere, and you can see that by the edge of the sun image being sort of messed around, that the yellow light is being bent up a little more than the red light, and then this little touch of green light is separated to the top. So it has to do with very stable inversion layers in the atmosphere, different density layers in the atmosphere. And you only see this at sunset. I think it might happen at sunrise, but it's only at sunset where you really get the heat difference. You can get the difference in the inversion layers. And you really, it only can really is usually only seen looking out over the ocean, because otherwise, you know, the ocean is so flat. Once you start getting into topography, it messes up the layers. I have seen it once briefly, not quick enough to take a picture.
Thank you.
Yeah.
Cindy Howard, I think you have a question there. Is that a question?
No, it's not a question. I just like the presentation. And I'm glad to know that it's not really a flat rainbow. It's really just the top of a big rainbow.
Yeah, you were there. Yeah, that was a real peculiar thing. I remember standing on the boat puzzling about that. But yeah, it was just the top of the rainbow.
Good. I think that's it for the questions. Fascinating presentation. We'll pass it back to Pam.
Well, you know, thank you very much. If I can just say one thing,
Yeah.
when this storm we're in clears out and we get clear, cold weather, that would be the time to start looking for these things. Look, you know, if you see the sun passing through, you know, faint clouds, look for halos, look for sundogs. Sundogs are mostly sort of later in the day, but halos would be any time. They're out there. All you have to do is look for them.